Hey guys, welcome back to chapter 14. In this video, we are going to continue our discussion of buffers, and we're going to talk about how they react when we add a strong acid or a strong base to that buffer. When we add a strong acid or a strong base to the buffer, the pH is going to change a little bit, right? So in this video, we're going to calculate that change in pH. So how much does the pH of a buffer change when a strong acid or a strong base is added? This is going to be a two-part problem. The first part is going to be quantifying how the relative amounts of the buffer change. And then the second half is going to be just the Henderson-Hasselbalch equation, using what we determined from the first part. So the first part of the calculation is going to be a stoichiometry calculation. We're going to calculate how the relative amount of weak acid and conjugate base change within our buffer. So we add a strong acid, it's going to react with the conjugate base, and it's going to make more of that weak acid. We're going to be able to quantify that change. Or I could do a problem where we add a strong base. It's going to react with the weak acid and make more of the conjugate base. And again, we can quantify that change. To do this part, we are going to use a table. So tables are just really handy tools for helping us keep track of or mitigate a lot of information. It is not an ICE table, but similar in format. Once we calculate the relative amounts of weak acid and conjugate base after it has consumed the strong acid, then we'll take that information and we'll put it into our Henderson-Hasselbalch equation. The best way to do this is just to dive into an example. For those of you that maybe have the notes printed out, I made kind of a last-minute edit. Instead of just using a generic buffer, I used an actual buffer. So if you're looking at your notes and it says HA, and then you look at mine and it says H2CO3, it's just because I made a last-minute edit. I think sometimes having an actual buffer makes it a little bit easier to see. So here's our problem. A 1 liter buffer solution is 0.1 molar H2CO3 and 0.1 molar HCO3. Calculate the pH of the solution after we add 0.025 of a strong acid. So the first thing we're going to do is we're going to write the equation for our buffer. Okay. So we're going to, let me get black here. We're going to start with the H2CO3. So this H2CO3 is our weak acid. I'm going to be very explicit about the parts, and you'll see why in just a minute. We'll always react that with water. And then on the other side, if H2CO3 is our weak acid, it's a proton donor. So the conjugate base on the other side will just be that compound with one less hydrogen. So this is our conjugate base. And then if this is our acid, water is behaving a little bit like a base, which is a proton acceptor. So the last piece of this formula will be that hydronium ion. Move these over because it's make it a little bit cleaner. All right. So the next step is going to be writing an equation, displaying the addition of the strong acid. So I'm going to use a generic strong acid. I'm just going to use this H+ to indicate that it's a strong acid. Okay. So which part of the buffer is that strong acid going to interact with? Well, just like positives attracted to negative, north end of a magnet is attracted to a south end of a magnet, opposites attract. So the strong acid is going to be consumed by our conjugate base. Acids and bases are attracted to one another. So this strong acid is going to be consumed by the conjugate base. And remember, this is a one-sided arrow. It's going to be a complete consuming of that strong acid. Every single molecule of strong acid we put in is consumed by the conjugate base. Okay. So when this happens, the acid is a proton donor, the base is a proton acceptor. So this is just going to kind of absorb into that formula, and we will be producing more of that weak acid. Okay. And remember, this is a one-sided complete thought. So that's our balanced chemical equation for each of these steps. What I'm going to do now is I'm just going to erase the ink on this slide, and I'm going to display a text version because it's a little bit cleaner. All right, so to solve this problem, we're going to have a new type of table that we use. So this new type of table is going to be for the second half of this equation. So our table is going to address this addition of the strong acid reacting with a conjugate base. So our table is going to look something like this. So we're going to, across the top, have this second equation, so strong acid, conjugate base, and should be 2. Our product. And what we're tracking is going to be this complete consumption. So on this side, remember, it's a stoichiometric. So we're going to have moles before we added our strong acid. We're going to have the moles that are added. And then we're going to have moles after the addition. So what this table is tracking is this step right here. How much of each of these did we have before we added the acid? How much of the acid did we add? And then how much of each of these did we have after we added the acid? So moles before. So before we added the acid, did we have any acid? No, we haven't added it yet. But we did have our some of the weak acid conjugate base. So how much of the HCO3 did we have? Well, it tells us right here in our problem, we had 0.1 molar. And how much of this H2CO3 did we have? We had 0.1 molar as well. Okay. Moles added. So this is going to be when we're adding our acid. So kind of a mute point here. We're not adding our weak acid. We're not adding our conjugate base. How much of the strong acid was added? That's what we see right here. Add 0.025 moles. Okay. Now we need to calculate what everything looks like after. Okay. So first we'll do our strong acid. This is a complete consumption. So every single molecule of strong acid I put in gets consumed by the conjugate base. So after it's all said and done, we've got no more strong acid left. Now we have to figure out what is going on here. So for the conjugate base, we started with 0.1. Remember that conjugate base is consuming the strong acid. So the amount of conjugate base is going to go down because we're using it to neutralize that strong acid. So the amount is going to go down, and it's going to go down by whatever was added. So it's going to go down by 0.025. Okay. It's consuming the strong acid. So I can do 0.1 minus 0.025. And at the end of all this, there's 0.075. Now, the conjugate base is consuming the strong acid to form the weak acid. So this is the whole purpose of the exercise. Take a strong acid and make it a weak acid. So as we're consuming the strong acid, we're going to get more of this weak acid that forms. We're producing it. So we started with 0.1, and we are going to add 0.025. So at the end, we're going to have 0.125. So this is the new piece. This is the hard piece. We are then going to take this information and we are going to plug that into step 2, into the second half. So the second half of this problem is taking our new values for the conjugate base, weak acid, and plugging that into the Henderson-Hasselbalch equation. Once we do that, we'll have our new pH. So here's the second half of this. We're going to determine the pH of this solution. I've given you on this slide the Ka. So we're going to take the negative log of that to get to pKa. Plus the log concentration of our base over concentration of our acid. So that's what we looked at here. And this is also another reason that I was explicit in the labeling, because it's going to help us put this into the right spot. So the concentration of the base goes on top. So the HCO3 is our base, so 0.075 goes on top. And then the concentration of our acid goes on the bottom, so the H2CO3 is our acid, so 0.125 goes on the bottom. Now we have it in our equation. We just need to plug it into our calculator and chug through it. So negative log of 2.5 times 10 to the negative 5th. This is 4.6. And then we're going to take the log of 0.075 divided by 0.125. So we're going to take the log of 0.6. So 4.6 plus log of 0.6 is negative 0.22. So the pH equals 4.6 minus 0.22, and we get the pH of the solution is now 4.38. So to summarize, we first wrote our balanced chemical equation for the buffer. Then we wrote a balanced chemical equation for the addition of a strong acid, so it's consumed by the base, producing more weak acid. We did a stoichiometric calculation for how the quantities changed when we added the strong acid. So before, added, after. And then we took the after concentrations, plugged them into Henderson-Hasselbalch to determine the pH of this buffer solution. I hope you guys found this helpful.